Start talking about vis braking. Now, vis braking, well, it's really a contraction. It's really viscosity braking. You're trying to reduce the viscosity of a heavy material. So if you think about it sort of qualitatively, you have this heavy, gunky kind of material. If you can break it down a little bit, then it'll flow a little bit more easily, and it'll have a lower viscosity. So vis braking, it's a relatively mild form of thermal cracking, and it's used to reduce the viscosity and the pour points of vacuum tower bottoms. The pour point, may have gone over it before, the pour point's an important quantity in certain types of fuels and other heavier material. You may not think it's important, but the pour point is very important, because if you have a vehicle such as a diesel engine, diesel trucks, if you're in a cold climate, the pour point has to be such that the material will flow at a cold temperature. So if it's minus 40 Fahrenheit and you turn on try to crank the engine and the fuel is actually solid, then you're not going to get very far. So pour point is one of those quantities that is important in heavier types of oil. Vis braking, there are two basic types, a coil or furnace type cracking and what they call a soaker cracking. And the process is here you see this is a soaker type. It's got a reaction chamber. This one, you put the material through a heater, you heat it up, and then you have a reactor where you allow the stuff to just sort of sit and soak, and there the reaction takes place. And then you go through and you have atmospheric fractionation and a vacuum column, and you produce some gasoline, light gas oil, and the vacuum gas oil and vacuum tar. So again, we've taken resid and we've managed to produce a little bit of gasoline that we can use, some light gas oil and heavy gas oil. We can use that for diesel fuels, things like that, maybe even for things like ship fuel. And all right. It reminds me of something. You know, on cruise ships, modern cruise ships, they work on basically a pretty heavy fuel oil, and the modern cruise ships, they burn many tons, something like 200 tons a day of heavy crude oil, and they bring in seawater from the ocean, and they basically do a distillation on the seawater using the waste heat from these engines, and they generate electricity from the turbines, and the electricity runs the propellers, and the waste heat actually distills the salt water into fresh water, and that provides all the fresh water that the people on the cruise ship actually drink. So it does go through purification and other steps, but basically, you know, you're drinking what's coming out of the ocean. But it's from an engineering point of view, it's actually quite a clever process. All right. Now, going back to our book, if you look in the directory, there's that PDF file with the refining processes, and it gives you a lot of information on vis braking. This is licensor here is Foster Wheeler and UOP, Universal Oil Products. They license many processes. But basically, they give you approximate conditions. If you have a certain type of feed and then certain types of products, and they give you a rough idea of the economics. So if you're doing some studies or something, you can use this kind of information to figure, is it worth doing this kind of unit? Is it going to help me in any way? And they do give you approximate utility costs here for fuel, electric power, and things like that. So you can do some simple economics. This one is Foster Wheeler's, let's see, this one, I know what he did. This one, you could read the text very well. The diagram wasn't so good, but I duplicated the page because the diagram's better here, but the text, for some reason, didn't come out very well. So it's the same page, but you can see the diagram a little bit better. All right, vis braking, this is the shell process, and this is the other type. All right, one was the sort of furnace type, and the other one is the soaker type, and this is the soaker type with the reaction vessel and this sort of thing. But basically, it's the same concept. It's the difference between the temperature versus the time of reaction. You can either heat the stuff up a little bit hotter, you have less reaction time, or you can heat it to a lower temperature, but your reaction time is longer. This sort of soaker process where you have the material held in the reaction area for a longer period of time. It has longer to react, but it's at a lower temperature, so the reaction rate's a bit lower. But ultimately, the products are fairly similar. All right, and again, this one has a better looking diagram than the other one. All right, so we need to have an idea of how common these kind of processes are. So here on the left, now these are a bit out of date, but even so, existing worldwide resid upgrading capacity. Now remember, we said was it 563,000 barrels a day was the biggest refinery in the continental U.S. So here you can see you've got a lot of barrels of capacity here. Okay, there's thousands of barrels per stream day. The coking of that quantity, coking is about 33%, vis braking 37%, and resid FCC, fluid catalytic cracking, is 7%. But then planned for the future, okay, we have coking, a little bit more here, and some hydroprocessing, 22%. So this gives you an idea of basically people are putting in these kind of units. You can see the capacity is going up quite considerably from year to year. Now, what does that mean for you? It means that in your careers you may well work on some type of resid upgrading type of equipment, because whether it's a delayed coker or a vis breaker or something like that, it's the kind of money-making process that refiners want to invest in, because they have this heavy material and they want to be able to process it into something useful. So now this is just the United States, so the numbers are less, but basically they're very similar. Now, if you notice, worldwide, coking was only about 33%, but in this country, it's more than double that. It's like 60%. So it's quite a lot of cokers out there, and you may wonder what happens to all that coke. You know, it's now this is an important slide for later on, really, but I wanted to bring it in here. We have competing processes for coking, and you can see the second one down, the delayed coking, about $5 a barrel. These are 1989 processing costs, so they've gone up, but obviously the relative amounts still apply. Flexi coking, which is a very nice, elegant process, but if you look at it, it costs twice as much per barrel. And even though flexi coking is, as we'll see, it's a very elegant process, but it's not installed that frequently because it costs twice as much per barrel to process it. And if you're processing many thousands of barrels, then if you pay twice as much to do processing, then eventually it's going to show up in your gasoline costs. So now other ones, this is hydrotreating, hydroprocessing, and the FCC, which we're not talking about today, but just to give you an idea. Vis braking is relatively cheap, but doesn't produce as much as delayed coking. So delayed coking actually gives you quite a lot for your money. It's not as expensive as flexi-coking, but you get more products from it. All right, so here we get to the real purpose of the topic, and we've only been going for an hour and a half here. So, coking, widely used resid upgrading process. It's a severe thermal cracking process. Completely converts resids to coke and more valuable liquid products. So we actually end up with a solid coke product, of the actual lumps of coke. And there are three processes available: delayed coking, fluid coking, and flexi-coking. These are both ExxonMobil processes. They're very similar to each other. There's a difference. But fluid coking and flexi-coking, there's slight difference in the processing, but they're basically both fluid coking processes. And now I tell you why it's called delayed coking. It's not because I've delayed telling you about it so long. The process is called delayed coking as the feed is heated in the feed heater, but coking is delayed until the feed is in the coke drum. Now, you may think that seems like a very strange way to name a process, but it's very important because you do not want the coke to form in the heater, because if it forms in the heater, it'll plug the tubes, and you have to shut down and get rid of the coke that's in the tubes. So the idea is you put it through the heater, you have a short residence time, a lot of heat, and you heat the stuff up, but it zips through the heater so quickly that it ends up in this coke drum, and that's where it accumulates in the coke drum, and that's where the reaction takes place. So the reaction is delayed until you end up in the coke drum. And if it's not delayed, then you're going to coke up the heater, and everybody's going to be very unhappy, because you're going to have to shut down and clean out all this coke from all the tubes. So, a strange name, but there is a reason for it. Now, delayed coking is a semi-batch process. So that means it's not completely continuous. There are parts of the process are continuous. The distillation columns run continuously, but the coke drums go through a cycle. There's like a batch. There's a whole sequence of things. Because if you think about it, imagine you have a hose pipe and you've got 6 buckets. You fill up the first bucket, and then the second bucket, and the third bucket, and the fourth bucket, etc. That's basically what you're doing with delayed coking. Instead of buckets, you've got 6 coke drums, and you've got the tube coming out from the furnace, and you divert which coke drum you put it in. But basically, you're doing the same thing. So as far as the coke drums are concerned, you're basically running a batch process. You fill the coke drum, the stuff reacts, and eventually you end up with solid coke in those coke drums. Now, as I say here, each coke drum is filled in turn with hot feed, and we'll go over this in a little bit more detail. And then the drum is opened to the fractionated tower, and the vapors from the coke drum are quenched so they're not too hot, and then they're fed into the fractionation tower, the main distillation column, a big column with all the side strippers, very much like a atmospheric crude column. Same kind of column, but it's designed just a little differently because of the coking products. And this is a typical delayed coking unit, and it's the feed comes in here into this main fractionator, the distillation column, and then it comes out the bottom and is pumped through the fired heater, and you add a little bit of steam for a couple of reasons, partly to help the situation so you don't coke up the tubes, but also what they call velocity steam. If you cut the throughput here and you reduce the velocity of material going through the tubes, as I mentioned before, you've got to go through that heater very quickly. If you stay in the heater too long, cokes up, you're in trouble. So if you cut throughput, you put in some steam to sort of blow the stuff through to make sure that your residence time in the heater is short enough. you come out of the heater, you see a 925 Fahrenheit, which is quite hot. And then you have this, like a three-way valve, and you go to one drum or the other. And then you fill up the drum. Let's say you fill up the one on the left. And then when that one is full, you switch the valve and you fill up the one on the right-hand side. And then you can see at the top there's another three-way valve, and that connects through into the fractionation tower. So once the coking reactions are going in the drum, then you have material feeding across, going into the distillation column, the main fractionator, and then you're doing the same kind of thing you're doing in the crude column. Right? This is basically another crude column, but they call it a main fractionator. Overhead, you've got a gas product, a light ends material. Just as we had with the crude column, we had an LPG type stream. See, unstabilized naphtha. The naphtha is gasoline range material. And then here we have a gas oil stripper, and we're producing gas oil. And you can actually, a lot of cokers have multiple side strippers. You'll have a kerosene stream, a light gas oil, a heavy gas oil, and then these are the vapors from these strippers go back into the main column. So you produce a range of products, but you can see this is kind of a tricky process, because you're pumping continuously here. So here we're continuous. Here we're continuous. You go through here, and then you've got these coke drums, and you're suddenly into a batch mode. So it's a sort of hybrid between a batch process and a continuous process. We call it a semi-batch. And then if you think about it, you see there's this arrow. It's showing coke coming out of the drums. Well, you fill up the drum, and you've got material now. You mustn't fill it too much, because if you fill it too much, you'll overfill. And remember what happens when you start overfilling stuff. Then remember from our safety topic. So they're very careful on how they fill these drums. They need to fill them high enough, but not too high. And then they allow the reactions to continue, and they've got it up to temperature, and this stuff is cracking away, producing the vapors that end up in the fractionator and end up as the products. Now here we've shown two coke drums, and eventually you will end up with solid coke in the drum. And you may wonder, how do we get this stuff out of there? And that's where a lot of the difficulties come in with delayed coking, because you've actually created a solid, and it's completely stuck in this coke drum, and you need to actually drill it out. And we'll see a bit later on how we do that. Now this is another delayed coking unit. Everything is very similar. The feed is coming in here and going up to the coke drums. But if you notice, there's a warm-up condensate drum here. And if we go back, it's just a little bit more detail added to this. Because when the coke drum is full, and once it's given its products to the distillation column, the fractionator, you then have this very hot coke. Now you could just let it sit there for quite a few hours and let it cool down, or you can inject some water, and you inject water to cool it down, and it also sort of cracks up the coke a little bit. And so on this other slide, you collect this water that comes back down through here and reuse it in the process. Now you inject steam into the main fractionator as well. There are various steam inputs to this. We're going to talk a little bit more about this later, but just to give you an idea, the coke drum is, typically these are quite big, 26-foot diameter, so that's the diameter, and imagine how tall these things are. The coking cycle basically has to add up such that you can run this thing continuously. And you have a certain period when you're pouring liquid in, you have a certain period when you're making the products, then you've got to put in some cooling water, you have to drain the stuff, you have to take the coke out, and you see a step there of heading up, and then purging, testing, and heating up. And we'll go through these in a little bit more detail. But if you think about it, imagine you had a pressure vessel with a flange on the top and a flange on the bottom, and you have a whole bunch of bolts there. You basically have a coke drum. You have to undo the top and undo the bottom and before you can get at the coke, because everything is sealed up. All right, so some of these steps are a little bit trickier than you might first think, and there are some clever solutions to how they've done these. All right, the decoking schedule, depending where you want to start in the cycle, basically, I say we go through these different steps, but let's start with number one here. The full coke drum is steamed out to remove any residual oil. A mixture of steam and hydrocarbon is sent first to the fractionator and later to the Cloquet blowdown system, where the hydrocarbons are recovered. So you basically start off, you put some steam through, blow out anything that's left in there. So you basically have a little bit of material you recover in what they call a blowdown system. And then you have to cool the drum, so you pour in enough water to cool it, allowing it to cool below 93 degrees C. Now, if you remember, we came in at was it 900 and something Fahrenheit, so 93 degrees C. It takes a while to get down there, and you generate a lot of steam when you start pouring in cooling water, and that's condensed in the blowdown system. And those blowdown systems have big banks of air coolers, low pressure system, and you've got to condense all that stuff back. Then draining, you have to drain the cooling water from the drum and recover for reuse. And then we have a step they call unheading. Top and bottom heads are removed in preparation for coke removal. Now, talk about a bad job, you know. If you're the operator, you have to go out there and take these two heads off. And this is actually quite dangerous, because if you imagine you've got hot spots in the coke and other things, you've been pouring water in there, but maybe it didn't hit all the right spots. So there's a danger when you undo the bolts that some gas is going to leak out. You're going to get a face full of hot steam, and that's not good. So they developed automated systems for taking out the heads and putting them back on. But they've actually improved upon that with a different system using special types of valves. They're basically slide valves, and they're especially designed for this particular service. And they don't actually take the heads off anymore. They have these special valves which will close and solve this problem. Then decoking. Hydraulic decoking is the most common cutting method. You basically have to cut this stuff out. Now remember, it's a 26-foot diameter drum, and it's a big, tall thing. So you have to drill down through there, and the basic method is to use high-pressure water jets to cut it out. And then the stuff will drop out the bottom, and then you end up with this coke. And once you've got all the coke out, you have to close the valves or put the heads back on. You have to purge the drum, pressure test it to make sure it's good, and then you've got to heat it up, because you don't want this drum that's basically fairly cool, but a little bit above ambient temperature. You don't want to be putting 925 degree Fahrenheit hot stuff in this very cold drum, because obviously the thermal stresses and things are going to be a problem. So you heat it up with steam and get it up to a certain temperature, and then you bring it online with that three-way valve, and then you start putting the hot material in again. Now, we'll go through some of these cycles. Here we've got A and B, and we've got this three-way valve. And you can see at the top here, there's the black part is coking. So you can see the A drum, the one on the left, we're basically coking for half the time, and then we switch to the B drum for the other half of the time. Yeah?
So how often do you need to do the coking on a weekly basis?
No, the coking is done every day.
Every day?
Every day. One of the critical things is the total length of the cycle. All right? Now, you can see here we've got 48 hours for the cycle. So that's 2 days, something like that. But this is only 2 drums. Now, lots of coking units have multiple drums, say 6 drums. And there is most coking units have an even number of drums, because as you can see here, you're filling one drum or you're filling the other drum. But they did build a coker in Bakersfield which actually has 3 drums, and it's like the $7 bills. You know, you don't see many of them. And this one, it does actually work, but it's so much more complicated, because people can conceptually, this one's working or this one's working, and they flip. But if you have 3 of them, you're kind of going around in a circle. It's the logic becomes so much more complicated, but it does work. I think one day they'll put in the 4th drum, but who knows? But anyway, you can see from the top there, this is how the cycle works. All right, so we have coking, steam out, cooling, draining, unheading, decoking, heading and testing, and heating. So you go through this cycle, and then you have multiple drums, and you have to keep working through this. Now, one of the things that they've done over the years is to sort of compress the cycle, because obviously the quicker you can get through this, the more production you can get. And one of the steps which takes time, this heading and deheading, where you were taking the heads off physically in order to get the drill in there. And there is a solution to that, and well, this one actually, just before we get there, this is the 6-drum solution. As you can see, everything is the same. Like the A and the B is identical to what we had before. Now we have a C and a D and an E and an F, and you see you're just staggered. Okay, everything is the same except it's shifted by 8 hours to the right for the C and the D, and another 8 hours to the right for the E and the F. So everything is going on in a cycle. But this also means when you operate a delayed coker, you have to really keep track of what's going on, because you've got 6 drums, and some of them are filling, some of them are cooling, some of them are draining. You have to know what's going on. So the operators have to be on the ball on this unit, because it's not like a unit where it all runs steadily, you keep the temperatures the same, and it just sits there and runs away. This type of unit, you have to be very careful what you're doing, because if you lose track of the cycle, then you pour the wrong stuff in. You can see that if you pour the cooling water in at the same time you're putting in the hot feed, that's going to be bad news. So you have to make sure you have all these steps right, and obviously you can't take the coke out until you remove the top heads or use these special valves. So it's quite an interesting process, but it's a process where the operators have to be aware of what's going on and aware that things are time critical. All right? You have a question? Yeah.
Now, when they're decoking it
Yeah.
and they're taking the coke out, it just goes in trucks. Is there like
Yeah. Basically, we'll see in a minute. It comes out through these conical sections. There's either a rail car underneath, or a hopper, or some other way of collecting the coke. And obviously, if you go and visit a coker, they're not the cleanest of units, shall we say.